Hello everyone, myself Dr. Upendra Kumar. I am Assistant Professor in Computer Science and Engineering Department, IET Lucknow. So, today I am going to discuss a topic B-tree deletion operation in design and analysis of algorithm. So, in our previous lecture we have discussed the what is B-tree, what are different properties of B-tree and how we can perform the insertion operation in B-tree. So, today we are going to discuss the deletion operation in B-tree. Now, just see, deletion operation in B-tree is more complicated than the insertion operation. Why? Because in B-tree if you are going to perform the insertion operation, so any new key would be always added to the leaf node of B-tree. While in case of deletion operation can be performed either from the leaf node or from the any internal node. So, if we delete a key from internal node, so we need rearrangement of the keys in internal nodes and also we need rearrangement of the child nodes. So, how we perform these operations that would be discussed one by one in this lecture. Now, this is the algorithm for deleting a key from node X in a B tree. So, basically there will be three cases. So, the first case is if you are going to delete a key which is in node X and X is a leaf node. So, this would be the case first. If X is the leaf node, so what we do? We locate that particular leaf node, and if that leaf node is having more than the minimum keys. So, what are the requirement of minimum keys in each node in case of B tree, that already we have discussed in our previous lecture, that every node should have at least t minus 1 keys or m by 2 minus 1 keys. So, if that particular leaf node is having more than the minimum keys, means more than m by 2 minus 1 or t minus 1 keys. So, simply we delete that key k from node X and we stop. But what happens if that node is only having minimum required keys, that is not having more than the minimum keys. So, what we do? So, in that case it would have three cases. The first case, first A case is that we will look for the left sibling. Now, just see, this is the node X and here there is a key k in node X, or we want to delete a key k from node X over here. Now, this node X is having only minimum keys, that is actually mandatory requirement for the B tree property. So, what will happen if you delete a key k from this? So, that property would be violated. So, how we can resolve that property? So, in that case we will look for the left sibling and the right sibling. So, at first A case actually we look for the left sibling. If the left sibling is having at least one more key than the minimum keys, so in that case we actually borrow a key from the left sibling. Similarly, the second 1B case, 1B we look for the right sibling also. If the left sibling does not have more than the minimum keys, so we look for the right sibling. So, what we do here, if left sibling is having more than the minimum keys means the number of keys should be greater than t minus 1 or m by 2 minus 1. So, m by 2 minus 1 or the t minus 1. So, what we do, the largest key present in left sibling would be pushed towards its parent, and the intervening key that is present in parent node, that would be pushed down to the node where we have deleted a key k. So, this is the first A case. Now what will happen? So, the key will be the problem, the deletion of the key from this node would be actually resolved when we this intervening key will come over here, and this the largest element of key would be pushed to the parent node. So, all the nodes will be following the B tree property and it will be okay. Now the first B case, once we do not have, so once we do not have more than minimum keys in left sibling, So, we will look for the right sibling. If the right sibling is having more than the minimum keys what? It should have more than t minus 1 keys. So, what we will do, again the smallest element in the right sibling will be pushed towards its parent, and the intervening key from the parent node will move down to the node where the key is deleted. The same process, the earlier process, just see here. So, the smallest element of this right sibling would be pushed towards the parent, and the intervening key would be moved down towards the node where we have deleted a key k, that is the x node. So, what will happen? So, all the properties of the B tree would be maintained, and we will stop here. Now, the case first C. Case first C occurs when with the left sibling as well as the right sibling both having only minimum keys. So, we cannot borrow any keys from these siblings. So, what we can do? See, in that case what we do? We actually merge, we create a new leaf node by joining a leaf node and the intervening key of the parent node, and then finally, we delete the key k from node x. So, all these operations will be discussed with example in further slides. Okay. Now, the second case, when we are going to delete a key k from node x and node x is a internal node. The case first was when the node x is a leaf node. Now, the case second says that the node, the key which you want to delete, which is residing in a node x, and node x is a internal node. Just see here, x is a internal node. So, how we can perform the delete operations? So, this would also have the three cases, 2a, 2b and 2c. So, now we will discuss the 2a case. So, if we want to delete a key from node x and x is a internal node, so we will first look towards the left child. So, basically y is a left child and z is a right child of it. Now, if its left child y has more than the minimum keys what? T minus 1 keys. If it has more than the minimum number of keys, so what we will do? We will find out the immediate predecessor k node of k in the subtree rooted at y. So, basically we will find out the immediate predecessor of key k. So, suppose it is k node. So, what we will do? We basically replace, what we will do? We will recursively delete k node and replace k by the k node in x. So, basically k will be deleted and k will be replaced by k node. K node is what? K node is the immediate predecessor of key k which you want to delete, immediate predecessor of key k which is residing in a left subtree rooted at node y. So, this is how this B tree violation would be resolved. Now, second B case. If suppose the left child y is only having minimum keys, it is not more than the minimum keys, then we will look for the right child to borrow that key k node. Okay. Now, just see, if the right child is having the more than the minimum keys, in that case we will search out the immediate successor of that key. Suppose key k is residing in this node x. So, we will find out a immediate successor k node in the subtree rooted at z. Now, what we will do? We will replace this k by k node, and again we will delete this k node from this subtree which is rooted at node z, right subtree. Okay. So, this will resolve the problem. Now, the second C case says that if the both left child and the right child both is having only minimum keys, left child y and right child z both is having only minimum keys, t minus 1 keys, then how we can borrow the keys from these two subtrees? So, in that case what we do? So, we merge k and all of z into y. So, what we do? The key k in x and z node, both these nodes are being merged into what? Y. So, that x loses both k and the pointer to z. So, x will be losing k here and it will also be losing the pointer to the z. Now, Y now contains m minus 1 and 2t minus 1 keys, that is the maximum possible keys the node can have in B tree. So, now Y will be having the keys of Y as well as Z as well as the K. Now, we delete the key K from node Y. So, now this would resolve the violation of the B tree property. So, all these cases would be discussed in further slides with some example. Now, case third. Case third actually is a case where the height of the B tree gets shrinks. When it happens, suppose if we want to delete a key k from node x and node x is the internal node. If you are going to delete key k from node x and node x is already having only minimum keys, so that property would be violated. Then again we will look for the key to borrow from its left child as well as the right child. So, now just see both the node x, node y and node z, or these three node is having only minimum keys. Then what we do? What we can do? Now, again we will look for the sibling also. Now suppose its sibling is also having only minimum number of keys, then what we can do? So, in that case what we do? We merge both the nodes y and z, and finally if you see the sibling is also having only minimum number of keys, then finally we merge what? Then we merge the node x with the sibling and along with the parent. So, this node x, what we do? We merge y and z over here. Then again next step is the node x, its sibling and its parent, all these three are being merged. So, when these three are being merged, the height of the B tree gets shrinks, the height of the B tree gets reduced. So, this is how we can resolve the violations that has been occurred while delete operation in case of B tree. Now, this let us discuss these cases one by one with some example. Now, case first A. Now, we need to delete a key k and which is residing in node x, and node x is a leaf node. Now, just see case first says that if the leaf node is having more than the minimum keys, so we do not care anything, we just delete the key from node x. Just see here, this is an example. Now, this is an example of B tree of order 4. Now, the value of t will be 2. Now, we need to delete 32 over here. Now, 32 is need to be deleted, it is residing in the leaf node. Now, this is the leaf node. Now, it has how many number of keys? 2 keys. What is the required minimum keys in any node? That is t minus 1. So, 2 minus 1 what? 1. So, each node should have at least one key. Now, it has one more key than the minimum key. So, since it is this key 32 key is residing in a leaf node and this leaf node is having more than the minimum keys. So, we can simply delete it without caring anything. Okay. Now, just see this 32 will be deleted simply, and now we will have such a B tree over here. Now, this node will be having only single key 31. Now, second case, first B case. When we want to delete a key k from node x and x is a leaf node, but the problem is that x is having only minimum keys. So, we cannot simply delete key k from node x. So, what we can do? So, we will look for the left sibling or the right sibling. Now, just see in this case we want to delete the key 31. Now, 31 it has this node is having only one key and the minimum key it should have only one. So, it has only minimum key. So, we cannot simply delete this key from this node. So, this is the case first B. Here what we see, we will look for the its left sibling and the right sibling, left sibling and the right sibling. Just see left sibling is having 2 keys, it means it has one more key than the minimum keys. So, we can borrow a key from this sibling. How we can do, how we can perform this borrow operation? So, the largest key of the left subtree moves up towards its parent and the intervening key from the parent moves down towards that node where we have deleted a key k. So, Just see here, so 28 will go upward and intervening node is what? Intervening node, that is its parent of 28 and 31 is 30. This intervening key will be moved down towards this node. Now, this 30 would be reached over here, just see. So, in place of 31, 30 will replace 31 here and 31 will be removed. Now, just see the largest element of the left subtree, it has been reached to the parent node. This 28 has reached to the parent node. Now, just see all the nodes are following the B tree property. So, this is what the result of case first B. Now, the case for C, when the node X is having only minimum key and its left sibling also having minimum key and right sibling is also having minimum key. So, how we can perform the Burrow operation? So, what we can do in that case? So, in order to delete, here we want to delete a node key 30 which is residing in node X over here, and its left sibling is having only one key, its right sibling is having only one key. So, how we can perform the Burrow operation? So, all these three is having only minimum keys, we cannot delete any key from any of the nodes here. So, in that case what we are doing here, so intervening node is what? 28. So, the parent of 25 and 30 is 28. Now, what we can do, we will merge this node, this node and intervening nodes also, intervening key also. So, and when finally by after merging we will delete 30. So, what will happen? So, if we are going to merge these three keys, so it will have how many keys? 25, then 20 and then 30. Now, we delete 30. So, it will have 25 and 28 and 30 will be removed. Just see here in this case, so parent is having only one key. In previous case it had two keys. We know that the B tree property says that if any node is having k keys, so it should have k plus 1 number of child nodes, means number of child nodes should be one more than number of keys. So, just see here, this node is having two keys. So, this node is having 3 child nodes. So, number of child nodes would be always one larger than the number of keys. Now, after performing the delete operation, just see this parent node is having only single key. So, definitely it should have only 2 child nodes, 1 plus 1. So, now this property is followed over here. So, now this is the way we can solve the first C case kind of problem. Now, we are going to discuss about the case second. Case second occurs when we are going to delete a key k from node X and node X is a internal node. The case first was for the leaf node. Now, this case second is for the internal node. So, if we are going to delete a key from internal node, so it would have 3 cases, second A, second B and second C. Now, second A says that if a key is deleted from the internal node X, so we will look for the left child and the right child. So, just see here, in this case we want to delete a key 33. So, 33 is to be deleted. So, this is an internal node. So, we will look for the left child and the right child. So, left child of this 33 is what? This one, 31 and 32, and the right child is what? This is the 35. Now, second case that say that first check the number of keys present in left child. So, this is your y and this is your z, this is your z, sorry, this is your z, this is your y and this is your z. Now, y is the left child. Now, left child has how number of keys? 2 keys. Our minimum key requirement is what? T minus 1, that is 1. So, it has one more extra key than the minimum keys. So, we can perform a Burrow operation. So, how we perform the Burrow operation? Just see here, the immediate predecessor of 33, immediate predecessor of 33 is 32. Now, this 33 is replaced by 32. This 32 will be moved up to the parent and it will replace 33 over here. So, now again what we can get? Just see here, so if 32 goes upward, so now 33 is deleted. Now, the parent node is having 30 and 32 two keys, and it has 3 child nodes 25, 31, 35. So, the B tree property holds here. B tree property says that if the key is having k number of keys, so it should have k plus 1 number of child nodes. So, there are 2 keys, so there are 2 plus 1 3 child nodes over here. So, this B tree property holds here. So, this is the second case 2A case. Now, what about the 2B case? So, in 2B case, if the left child y does not have more than the minimum keys, then we look for the right child. If the right child is having more than the minimum keys, then in that case the same procedure is followed, but here we find out the immediate successor. Here 32 was the immediate predecessor of the 33, but in second B case we will find out the immediate successor. So, it may be 35, it may be something else. So, that would be replaced by the successor, and that particular key would be deleted, and finally, we will get the resolved B tree. So, this is the second B case. Now, second C case, when you want to delete a key k from internal node x, and both the child nodes y and z is having only minimum keys. So, we cannot perform borrow operation, we cannot borrow any key from either from the left child or from the right child. Then what we can do? Just see here, this is a B tree and we want to delete a 30 key from x, and for 30 left child is 25 and right child is 31, y and z. Just see, both y and z node is having only minimum keys, only one keys. So, we cannot borrow any key from these child nodes. So, what we can do? So, in that case what we do? We merge this key k along with this node z into y. So, then what happens? So, basically this parent node loses what? This parent node loses the key k and also the link with the node z. Then finally, then we delete z and also we delete a key k from this node y. Just see here. So, 30, 31 and 25 are being merged, and then finally we remove 30. So, what we get? Just see here, the 25 and 31 they are become actually in a single, they have come into a single node here, and 30 is key is deleted. Now, just see, earlier this key was having 2 keys, this node was having only 2 keys. So, 2 keys means it should have 3 child nodes. Now, after performing operations, this node is having only 1 key. So, it should have 2 child nodes. Now, it has 2 child nodes. So, now B tree property holds for the second C case. Now, this is what the second case, second A, second B, second C. So, we have discussed till now first A, first B, first C with example, second A, second B, second C with example. Now, we are going to discuss the third case where the B tree gets shrinks, the height of the B tree gets reduced. How? Just see here. Here this is a B tree of order 4. So, minimum number of keys are required t minus 1, that is 1. So, each node should have the minimum number of keys, how much? 1. It cannot be less than 1. So, just see here, this is the node x and the key k 10 is stored over here, we want to delete this 10 from this node x. So, what will happen? Node x is already having only minimum key. If you are going to delete this 10, so what will happen? It would violate the B tree property. Now, we will look for the left child and right child also. Now, left child is y, right child is z. Both of the child nodes is also having only minimum keys, only one key. So, we cannot perform a borrow operation over here. Then again what we can do? We can look for its sibling also. So, its sibling is what? 35. Sibling is also having only minimum keys. So, again we can not perform the borrow operation from the sibling also. So, what we can do? So, in that case what we do? We merge these y and z into a single new node, and then again if you want, and then again both 20 means parent, its sibling and this node x itself, all these 3 are being merged, and after merging we delete this key k from node x. Just see here, Now, we are actually what we are going to do here, we are going to merge this node x with its sibling and with its parent over here. So, what we get here, finally we get here. So, after merging we just see the parent node, the root node is having 20 and 35 and 10 has been removed, then 5 and 15 has been merged. Just see here B tree property holds. How? This node is having 2 keys and it should have how many number of child nodes? 3 child nodes. Now this B tree property holds over here, and just see earlier the height was 2 and now the height becomes 1. So, number of total edges present in the longest path that decides the height of the B tree. So, here the height is 2 while here the height becomes 1. So, this is how we can perform delete operations for all these 3 cases. Now, this is an example, combined example, where we will see all the different cases. This is a B tree of order 6. So, how many number of maximum keys? 5 and minimum keys 2. So, each node should be having minimum 2 keys and maximum 5 keys. Now, here we want to delete a key f, and f is residing in a node which has 3 keys, which is more than the minimum keys. So, we can simply delete, and this is residing in leaf node. So, we will simply delete it. Just see here we have deleted f here. Now we next question is we need to delete m. So, m is residing in internal node and its left child, for m left child is jkl and right child is no. So, left child is having more than the minimum keys is 2. So, it should have more than 2 keys. So, it has 3 keys. So, it would be replaced by its immediate predecessor. So, predecessor for m is L. So, this m will be replaced by L over here. Just see here m has been replaced with L over here. Now just see we want to delete G over here. So, now for G left child is DE and right child is JK. Now, both is having only minimum keys. So, this is basically the first C case. So, what we will do, we will merge these 2 nodes and then we delete we perform the delete operation. Now, just see both these nodes have been merged over here. Now, finally, just see we want to delete D over here, since this node is having more than the minimum key, so and leaf node, so it would be simply deleted. Now, just see the height of the B tree should be maintained as minimum as much possible, since each node can have maximum 5 keys. So, here if we merge these 3 nodes, so this height of the B tree would be shrinked over here. So, just see here we have performed a shrink operation and all these 3 nodes have been merged and we have a final reduced B tree. So, this is how we can perform the delete operation in B tree. Finally, we will discuss the analysis of deletion. So, deletion of a key k requires basically a one downward pass. So, and most of the keys are on the leaves. So, it requires only one downward pass. So, unit time, and when we delete a key from the internal node, so may have to go one step up to the replace the key with its predecessor or successor. So, it would basically require a height of the tree time. So, complexity comes big of h equal to log of n base t, where t is the minimum degree of B tree. So, that is all about B tree. Thank you very much.